about how the electron sharing is taking place in ferrocene?
Yes, sir. Can you please make the question once again?
Can you share how the electron sharing is taking place, how the bonding scenario is in ferrocene?
Okay, sir. Here the cyclopentadiene, two cyclopentadiene actually in staggered conformation, they make sigma bond with Fe2 plus ion. And we know that cyclopentadiene is strong sigma donor and weak acceptors. So they put the electron towards Fe and but do not take the electron from Fe. They just give the electron to Fe. So that's how the entire molecule is Lewis base. And as far as bonding is concerned, here it is a organometallic compound. So here we can see that organic ferrocene molecule and the Fe makes bond. So we can say that it is a very good organic organometallic compound. And here the ferrocene, we know that the ferrocene cyclopentadiene, the hydrogen is very much acidic. So after abstracting the hydrogen, it will be very much aromatic in nature. So thus it is, so that's the reason for being the stability of ferrocene, because the cyclopenta, the CP ring is very much aromatic, which makes the molecule very much stable. That's
Getting back to the bonding scenario, right? So each cyclopentadiene basically is like cyclopentadienyl anion, right?
yes, sir. Yes, sir.
So each ring will contribute how many electrons?
6 electron.
6.
6, right? So you have
Yes.
2 rings, right?
2 rings. Yes.
Yes.
So then it is how many electrons together?
12 electron.
12.
And iron is in which oxidation state? You mentioned that.
2
Plus
plus
2.
2 plus. 2
That
plus.
means how many electrons?
6. 6.
6 electron.
And
D6.
that means total how many electrons?
18. 18.
Now, can you tell me that if this 18 electron has got something to do with the stability of this species? Just
Sir,
intuitive.
Sir, inert structure basically 18 field octet fields configuration.
I don't understand these complicated words. Can you make it very simple? What is this octet and what is 18 so special about? And perhaps that from that angle explain the bonding scenario. So why ferrocene is stable?
can I tell, sir?
Sir,
Yeah.
sir it basically attains the 18 electron configuration.
What is special about the 18 electron configuration?
As a inert structure basically, structure of inert gases. So it is stable, I guess.
Why inert gases have 18 electrons? Helium is an inert gas. It has 2 electrons, right?
Yes, sir.
Sir, because sir, 18, in case of 18 electron, the entire shell is fulfilled. So it does not need an electron or give an electron to make the electron half filled or full filled. So it already has the completely filled shell. So that's why 18 electron is considered as inert environment, inert molecule.
So very simply is that you have the SP and the D, right? So S is
Yes,
2,
yes.
D is 6, and
Yes.
D is 10. So
Yes.
Yes,
can you feel
yes.
this?
Yes, sir.
Okay, Porna, Amitabha, if you have, I think it's fine.
No, Shomajit, I am fine.
I'm also fine. I think the next 2 people have also joined.
Okay, then thank
Okay,
you, Shayon and
thank you.
Chitro. Thank you.
Thank you.
Okay, sir. Thank you, sir.
Priyanshan Daya, please make sure that you finish within 7 minutes, okay?
Okay. Good afternoon, ma'am. This is Priyanshu, and
Please
this
make it full screen, Priyanshu.
okay. This is Priyanshu, and this is my partner Daya, and we are going to present a paper on a novel palladium-2 complex with ferrocene-based ligand synthesis, extracrystallography, and in vitro anti-cancer activity study. Introduction: Cancer has been one of the most threatening health issue to human life and well-being. Effort have been made to anti-cancer drug, among which platinum-based are most involved in clinical medication. As the side effect and drug resistance of platinum-based drugs remain a tricky issue, increased interest have been diverted to other organometallic anti-cancer drug candidates such as palladium-based drug. A series of palladium complex and cyclopalladated compound have been reported for the synthesis and anti-cancer activity. Structure activity relationship studies have revealed that the N group, bridge ion, and monomerization most affect anti-cancer activity, while the impact of the aryl group directly attached to palladium is minimum. Studies of the anti-cancer mechanism of some palladium-based compound reveal various pathways, among which different structure might induce cell death through different mechanisms. Some compound interact with thiol group of protein on various organelle membrane, and cell apoptosis is triggered by membrane permeabilization, and other compound inhibit cell proliferation by interacting with DNA. Due to unique features, ferrocene and its derivative are used as an alternative group in the design of some anti-cancer drug. Some ferrocene derivatives are capable of generating reactive oxygen species and thus induce cell apoptosis. Some are reported to have interaction with topoisomerase and lead to DNA cleavage. The potential of palladium-based compound as promising anti-cancer drug candidate is largely hindered due to lack of the knowledge of their mechanism. Therefore, most distinct ferrocene derivatives and their palladium complex need to be synthesized, and their anti-cancer mechanism need to be explored. We are here to synthesize a novel palladium-2 complex of ferrocene skip base with a trans configuration that is distinct from previously reported cyclopalladated ferrocene derivative. Such structure is rarely reported for anti-cancer activity, which could provide some clue for the structure activity relationship study of ferrocene derivative and then palladium-2 complex. Here is the synthesis of the compound, and in the picture are given below given the reaction condition. First, the ferrocene skip base was obtained by the condensation reaction of ferrocene carboxylate with 1 amino piperidine in anhydrous toluene as brown powder at a good rate. Skip base was then mixed with Na2PtCl4 and NaOHC.3H2O at 2:1:1 molar ratio in dry methanol at room temperature for 24 hours. Palladium-2 complex was obtained by column chromatography separation with moderate yield. The complex was characterized by 1H NMR, 13C NMR, and ESIMS, single crystal of compound FC PPD2 were obtained by slow evaporation of solvent from CH to Cl2. Daya, from here.
This is the crystal structure of our compound presented as OR-TEP diagrams. It can be seen that palladium atom is bound to 2 chloride anions and 2 nitrogen atoms of 2 ferrocene shift-based molecules in a trans fashion. The bond angles of both nitrogen, palladium, nitrogen and chlorine, palladium, chlorine is close to 180 degree. This molecular structure adopts a square planar conformation with palladium atom lying within the plane defined by the 2 chlorine and 2 nitrogen atoms. And also this structure is centrosymmetric with a palladium atom being the inversion center. Now, IC50 value is that concentration of a drug that reduces the activity of another drug to an enzyme by 50%. So when they compare the IC50 values of ferrocene compound against selected cancer cell lines with cisplatin, Our ferrocin compound showed excellent performance on 3 cancer cell lines like MCF7, it's a breast cancer cell line, and MCF7 ADR and ACHN with anti-cancer activity of 14-fold, 5-fold, and 25-fold higher than that of cisplatin respectively. Besides, ferrocin compound also showed cytotoxicity against human hepatocellular carcinoma cell lines like SKHEP1 and HCCLM3 with activity of 2-fold higher on SKHEP1 when compared to cisplatin. So here, ferrocin compound showed good activity against multi-drug resistant cell line, that's MCF7 ADR, which indicates that this complex may have different anti-cancer mechanism which circumvents the efflux effect of PGP protein. Next slide. Now, this figure shows the effect of ferrocin compound on cell apoptosis, that is the cell death. MCF7 was incubated with ferrocin compound at 0, 5, and 20 micromolar respectively, and the flow cytometry was done. We can see here the percentage of cells in apoptosis and necrosis, that is in the upper right quadrant, has increased when concentration was increased from 5 to 20 micromolar, which suggests that the ferrocin compound induced apoptosis and caused a significant increase in apoptosis in a concentration dependent manner. Now, going to the conclusion, a novel palladium complex with a ferrocin-based ligand was synthesized and thoroughly characterized. Its configuration was confirmed by X-ray single crystal diffraction. It was revealed that our compound was anti-proliferative towards 5 cancer cells with potency and drug safety superior to cisplatin. So at last, the flow cytometry analysis indicated that the complex exerted anti-proliferation activity through induction of cell apoptosis. Thank you.
Thank you, Priyanshu and Daya. You didn't mention the which journal, which paper, which published in which journal. I was trying to follow that.
It is we found.
You have mentioned the DOI, but DOI doesn't.
We found in the ScienceDirect.com in Science.
But it must be published in the Science Direct. But what is the name of the journal? That is what I'm trying to.
Inorganic.
Means 1 minute.
Anyway, it's okay.
Means it was.
Let us come back to the
LSB means
inorganic chemistry communication. Okay. So let us come back to that. Your presentation. The cytotoxicity or the activity against the cancer cell, whatever you say, is due to the palladium core, isn't it?
Yeah.
It's a palladium. You mentioned it very clearly. Okay.
Yes.
Yes.
Palladium chloride. That is a core. Now the question is, you have decorated that molecule with the ferrocin derivative. Okay. So what would have happened, or how do you compare the cytotoxicity of this molecule when if you replace ferrocin with a phenyl group? Definitely, they have discussed this in the paper.
If we discuss means it. If we,
you understand my question? We are just trying to understand how ferrocin has improved the activity. If ferrocin has improved the activity, how and why? That is basically we are trying to understand.
In the paper, it is written that the mechanism of this reaction has not been confirmed. But I think it will be efficiency will be reduced. I think it will not be that effective if it will replaced by the phenyl group, and because.
Listen, let me ask you the other question. This is a very basic question. Why the palladium chloride, this sort of molecules, palladium derivatives, are cytotoxic to cancer cells or human physiology? Why? How they act actually?
They react with the
by binding with the strands of genetic material, that is DNA.
Yes, you are right, but binds to the strand of the DNA. That's right. But how they interact with that DNA strand? Any clue to the lability of these chlorides?
Means I think the means
Any idea about this, how cisplatin works?
means cisplatin and means yes, cisplatin means the platinum that means that binds with the DNA and that causes apoptosis.
Yeah, but the question is how it binds.
How it's bind cisplatin. Mm,
You need to look at it. You know, these chlorides are basically highly labile. The moment it goes to the human physiology in terms of the bloodstream, these chlorides are being replaced by a water molecule, and that happens not in one step. There is a sequential manner. But once the diaco complex is formed, then they start reacting with the nitrogen of the nucleotides, one of the nucleotides. You need to see. And when they bind, they actually change the conformation of the DNA helix. Anyway, so Parna and Shomojit, any question?
No, I think I'm fine.
It's okay.
Okay. So Priyanshu and Daya, I think you are done. Please sign off.
Thank you.
Yeah. Okay.
So, Dashim and Kamlek, you can start your presentation.
Okay. Come, let's start the second.
And please try to be maintain the time, right? 7 minutes.
Sorry. Ma'am, the screen is visible, right? Hello.
Yes, it is visible.
Make it full screen. Okay.
Okay, shall we start?
Yes.
A fine evening to all the respected professors. This is presented by Kamlik Chatun and Nasim, my friend Nasim Siraj. So the topic which we have chosen is thermochromism. The title is reversible thermochromism in hydrogen bonded polymer containing polydiacetylene. Now, why we have chosen, what is this polydiacetylene? It is basically a polymer made out of diacetylene by topochemical reaction. The suitable condition for polymerization is that the chain needs to be in a 45-degree angle and the distance between the chain should be, the diacetylene chain should be 5 angstrom. So they self-assemble and form the polymer. Now, why we have chosen this PDA, that is polydiacetylene, is that it is an amazing optical polymer that is after polymerization, it forms a deep blue color, which is non-fluorescent. But after getting in certain condition, it forms fluorescent red color. That certain condition is exposure to heat, that is thermochromism. It shows a wide range of application, that is biosensing or identification of organic, volatile organic ink. So that will be discussed later in this presentation. Now, the motto of this presentation or the paper was that it is basically a chemical engineering. That is to explore the possibilities of polydiacetylene. That is, in the head chain of this diacetylene, they have added this terephthalic acid that is the hydrogen bond of this terephthalic acid is of our use. That is, because of this hydrogen bond, we all know that polydiacetylene is irreversible. It shows irreversible thermochromism, but because of this hydrogen bond, it will show reversible thermochromism. We will see why. Now this is the structure of our interest. This is the terephthalic acid which is added to the head of the chain. This is the chain. This is the side chain. This is the side chain. This is given here. Now this polydiacetylene are always in a stacked layered structure. Now you can see from this. This is the hydrogen bond which we were talking about. This is the carboxylic acid. Now in normal PDA structure, what happens is they are the stack layer is due to the pi interaction. Now when the heat is applied, that is it goes from blue color to red color due to thermochromism. When the heat is taken away, that there is a destabilization in the pi structure. So when the heat is taken away, that that pi interaction is destabilizes and they cannot come to their original conformation. Because of that, this one is irreversible. The thermochromism is irreversible. Now what this hydrogen bond is doing is, because of this hydrogen bond, even if we take away the heat, the tendency to form the bond again helps or makes this PDA to come into its original position, so that even when we take away the heat, that is from blue to red color, and when we take away the heat, it comes into blue color. This is how the color is changing. This is the blue color. This is the CC single bond is rotating, and we are getting this red color. Now what they have done here is, they have taken this Da1 and Da2 and monomer Da1 and Da2, and they have put into hexane. They are soluble in organic compounds, so they have put in hexane or chloroform. So what they have, from this graph we can see that all the polymers are quite identical. So they have omitted all the polymers and they have done the experiment for Da1. So for any experiment, or for us to identify any polymer or any molecule, what is the most important thing is the absorption spectrum. So they have taken the Da monomer and they have put into chloroform solution, and they have also put in a dispersion medium, and they have put into a spin coated film. So what they have done is, they have exposed it into UV light of for 20 minutes. That is the 254 nanometer UV light. So what first the emission color is blue, that is it is being absorbed at 600 nanometer. So when it is exposed to UV light, the absorption shifts to shorter wavelength, and red color is seen. Now for the thermochromism part, my friend Nasim will take up from here.
Good afternoon. Let us now look into the thermochromic properties of PDAs. Now this graph represents thermochromic color changes of PDA1 at indicated temperatures. Here the blue foam, which gives a band at 600 nanometer, is progressively disappearing, and the red foam is appearing as the temperature increases. On cooling, the blue foam reappears in a completely reversible manner. This remarkable thermochromic behavior was not observed in PDAs during that time. Change. Now, what is the origin of this thermochromism? Change slide. Change the slide. Okay. Now, what is the origin of this thermochromism?
The last.
This graph shows the differential scanning calorimetry data for 4 different molecules, that is 2 reactants and the 2 polymers. Here the 2 peaks indicates that the properties of the rigid backbone layers are considerably different from the side chain layers. Here the low temperature transition corresponds to disordering of the side chains or side chain melting, and the high temperature transition corresponds to the rotation of the rigid core or the melting of the whole molecule. Here differential scanning calorimetry data suggests that the thermal stimulus gives the side chains enough energy to impose a mechanical strain on the PDAs by rotation around the single bonds between the methylene units. Although such movements of the side chain must be restricted so that the the necessary crystal integrity for the reversibility is maintained. Here, theoretical calculations also says that such a side root motion could induce a change in the electronic structure of the PDA, which could be the possible reason for this thermochromism. So the origin of this thermochromism is still unclear. change. Now let me wind up this presentation by stating some of the conclusion and scope of this paper. First of all, the experimental data was not sufficient to construct a molecular model of PDA showing the spatial arrangement of all groups with respect to each other. Also, the combination of double hydrogen bonds in the terephthalic acid course and diacetylene side chains enabled a topochemical polymerization under UV light and allowed us to prepare this PDA in different mediums. And synthesized PDA was exhibiting this reversible thermochromism, which was remarkable. Also, the PDAs are used as sensors for biological detection or coating for these optoelectronic applications, since they can form stable and ultra-thin polymeric films. Also, this thermochromic properties expands the scope of PDAs for various other applications. That's all for this presentation. Thank you so much.
Shomajit?
In fact, I did not get it clearly. So you showed a work and it is not clear. So I still do not understand what is the logic of this thermochromism. You said you left it open because a lot of things are known with the PDA thermochromism, right? Why did you choose this paper, which is inconclusive? Because what the normal reason for the PDA thermochromism is, unless you graft some side chain modification, which people normally do, is because of the rearrangement in the distribution of the double bonds. Okay, so that leads to different colors and that also different entanglement length in the side chain. This is known, but I don't know what paper. What is the reference of this paper? Because I really
actually this normal PDAs, they will be like exhibiting irreversible thermochromism. So here they are modifying this by some side chains and
by adding that terephthalic acid from that hydrogen bond.
And
no,
due
but
to that hydrogen bond, they are exhibiting reversible thermochromism.
No, but the reversible thermochromism, for example, is known even in modified PDAs. That's what I was trying to say, right? So there are several ligand modifications which you do, and this is because of the difference in entanglement length change in the side chains, or in the difference in the charge transitions among the ligand groups, right? But here you said that it is not clear why the thermochromism takes place. So this is inconclusive in my opinion, right? So why did you choose such a paper? Because if you just look for high temperature thermochromism in PDA, which is very strongly explored, right? A lot of explorations have happened with this type of, polyacetylenes, which are conducting thermo and as well as electrically conducting polymers. So what is the paper, by the way? I did not get it. Which
No,
reference?
like from the paper, actually the paper was in the paper it was not clearly given, so later we had
No, can you show me the reference? Can you show me the reference?
Okay, the reference. Should I show this one?
That paper. Yeah, I
do you have the link?
I can present. You just show presenting.
Okay.
Because to me it's an inconclusive result. It's not a conclusive paper because there are so many systems. So my question is, why did you choose this when it is inconclusive? That is what I.
But you should have given the proper reference of the paper in the presentation also.
Can you see now?
Yeah, it's an Angawante, right?
What?
Looks like an Angawante Shimi paper.
Yes.
I didn't get you.
2004 or 2005?
Yeah, 2004 or something.
So it's very old. So it's very old. Okay.
Yeah.
Yeah.
So
Because you should, I mean, for example, if you present something, you should present the state of the art, which is known, right? So not something which is not known and old, right? This is very old because modern day the people know about this thermochromism. Anyway, so this is just a comment, because this is the normal reason is because of the distribution in the side chain, the exchange interaction in the side chain. That is how people tune it, and you can modify the spacers in the side chain. That's how you can change, and you can induce reversible thermochromism in PDAs, and also in some cases polyanilines and things like that. Okay.
Also,
So this is normal.
It means that double bond is of interest, right, sir?
Right. It is the double bond, and then modifications around the double bond, and you can imagine you can change the donor groups and the acceptor groups around the double bond, and also the distribution of the double bonds around the main chain, right? So that changes the interaction, and that changes the color with the temperature. Yes, that is the simple logic, and a lot of work has been done. So you can look
Okay,
it.
so that acid is only helping it to maintain its like structure, right? And that double bond is which is helping it to change the color.
Yeah, so you are using in this case terephthalic acid, and the terephthalic acid will have different kinds of electron removal or donation with the side chain, and then that will change the gap between the conduction and the valence band, and that will change the color. So these are all known, right? And so a lot of work has been done. So when you say this is not known, this only it reflects that you did not do the background search properly. Okay, so that is all I want to say. So be careful before you present something and say this is not known. Right?
This was so.
Yeah. Okay, I'm fine. Thank you. Amitabh,
I'm fine.
Thank you. It's done, right?
Yes.
I'm fine.
Thank you.
Onna, if you have any question,
No, it's okay.
okay. Or they can sign off.
So we just discussed a lot.
Thank you.
Thank you so much.
Thank you, sir.
Thank you. Vidipta and Rohan, you please start your presentation
Yes, ma'am.
and maintain the time.
Good afternoon, respected professors. Today, I, Vidipta, and my friend Rohan is going to present on the topic layered double hydroxide based on the paper titled as Hollow Structured LDH Structure Evolution Induced by Gradient Composition. And we want to thank our professors for providing us with such a nice opportunity. At first, what is LDH? Layered double hydroxide, that is LDH, the cluster of positively charged ionic lamellar inorganic material, also known as anionic clays. The metal cations octahedrally coordinate with hydroxyl groups to form LDH structure. The edges of octahedra forms infinitely large structures, and the hydroxyl groups cover both the surfaces of each layer. In LDH, the metal cations are a combination of divalent and trivalent cations. The most common divalent metal cations are magnesium cation, nickel cation, cobalt cation, and metal trivalent cations are aluminum cation, iron cation, etc. The trivalent cations forms positive charge residue in their places in the octahedra. In this diagram A, we can see the hydroxide layers with interlamellar space in between which contains anion and water molecules. Further zooming in, we can see in the lattice picture, metal cations are surrounded by hydroxyl anions. This is the SEM picture of LDH nanosheets stacked together. Now discussing about role of LDH. At first, from the general properties, we can see LDH have lower interlayer space, large specific surface area, high chemical and thermal stability, ability of intercalating different anions, in a sustained manner, be it in organic, biomolecules, and also genes. Also, anion exchange capability of LDH is due to the freedom that anions have to travel through interlayer aqueous medium and steric constraints. These are, in short, properties of LDH. Due to time strain, I am only discussing about the scope and application of catalysis property of LDH. LDH material acts as supporting surface and its role lies in enhancement of catalyst selectivity, although it doesn't actively participate in reaction steps. LDH are induced to transform into new material. LDH can act as absorber in catalytic environment by acting as a reservoir. Loss of structural integrity. Also, LDH nanosheets can be used in flame retardant, stabilizer, supercapacitor, biosensors, targeted drug delivery, and even can act as gene carrier. Now I would like to pass over to Rohan for the next part.
The design of any nanostructure matters because it dictates the efficiency in catalysis. Our target is to synthesize hollow structured LDH to improve catalytically active sites for oxygen reduction reaction, or in short, ORR. For that, first we need to develop a potential platform for the construction of a hollow structure. In LDHs, bivalent metal cations and trivalent metal cations coordinate with hydroxyl anion and nucleate to form positively charged laminates. But the question is how to select the two metal ions. For that, we consider distinct KSP of them because KSP represents the maximum extent that a solid dissolves in solution. So, by different dissolution, the LDH laminates would presumably form core shell structure under the condition of urea hydrolysis. Now, why to choose urea hydrolysis? Because there is a crucial role of pH. As we have seen in the Gibbside experiment also, urea hydrolysis makes the solution alkaline, which helps in the selective etching of the cations by OH-, thus avoiding a second modification step. So they followed co-precipitation method. So accordingly, they first mixed isometric amount of cobalt nitrate and aluminum nitrate with urea solution, stirred, passed to autoclave for 0.5 to 6 hour period to maintain high temperature, and centrifuged for separation. The mechanism is as follows. First, hydroxyl ions generated from the urea hydrolysis coordinates with Al3+ and produces aluminum hydroxide. This aluminum hydroxide, AlOH3, behaves as the crystal nucleus for further epitaxial growth of cobalt aluminum LDH. Then these excessive OH- ions continue to react with AlOH3 and form soluble AlO2- in strong alkaline medium, leading to the formation of LDH nanoring. Also, as CO2 goes up, further workload has been reduced. Now, as we can see here, after 2.5 hours of reaction, the pH becomes almost constant, and at 1.5 hours, the central hole started to grow at approx around pH 8. But the question now is how much will this continue to grow? Otherwise, it will reach the edge. So to address that, the ratio of ring diameter and the outer diameter were compared at different reaction time, as we have seen in this picture. Now, a larger change in the diameter of the hollow ring indicates that the dissolution of the cobalt aluminum LDH core is faster than the further epitaxial growth of the LDH. The proposed OH etching Al3+ is verified by directly introducing dilute NaOH in the cobalt aluminum nanosheet. So, by now, we have understood that the selective etching of OH- gives our desired nanoring shape. So, the immediate next question comes: which metal cation resides inner side, and that is at the boundary of the pore and nanopore, and which cation lies towards the edges. From KSP data, we can see that aluminum has lower KSP. So the coordination between aluminum and OH- is thermodynamically more favorable compared to cobalt 2+ and OH-. So there should be a gradient composition with aluminum 3+ rich core. Further characterization using UV, ICP, OES, TEM also supports that thing. As we can see, the color disappears gradually as cobalt 2 plus gets dissolved, and with the progress of the reaction, LDH forms, that is the layered structure, so the color reappears. If we analyze further with inductively coupled plasma optical emission spectrometry, that is ICP-OES data, here we can see that the cobalt 2 plus and by aluminum 3 plus ratio increases in solid sample with reaction time. Thus indicates that Al3 plus cations are more favorable to coordinate with the OH minus ions than cobalt 2 plus at the early stage of urea hydrolysis. At 1 hour reaction time, the nearly zero absorbance of cobalt 2 plus indicates the full interaction between cobalt 2 plus and OH minus to form LDH structure. After that, the hydrolysis of excessive urea led to dissociation of the core. Then again, the concentration of cobalt 2 plus increases, so absorbance gets higher and the color comes back. And the TEM images confirms that the LDH maintain the integrated regular hexagonal nanosheet structure. And with time, the nanopore appears in the middle, but these are irregular shape. And the outer diameter continue to grow, but this maintains the regular hexagonal shape. In the element mapping through EDS, that is energy dispersive spectroscopy, the increased cobalt aluminum ratio from the center to the edge reveals the gradient distribution of cobalt 2 plus and aluminum 3 plus in the nanosheet, where aluminum 3 plus enriches the core and cobalt 2 plus enriches the edge. Now, they use ORR activity as a probe reaction to study the structure catalytic activity relationship of the nanoring. As we can see here, the nanoring exhibits a higher ORR onset potential at around 0.88 volt and a higher half-wave potential approximately 0.74 volt and over 110 millivolt compared with the nanosheet. This indicates the higher intrinsic activity of the nanoring. Now, this figure below reveals the enlarged electrochemical surface area of the nanoring, which suggests that more edge site could be exposed as active sites in the nanoring compared to the nanosheet. In the capacitance performance, we can see nearly 50% increased capacitance for the nanoring, which indicates that more active metal sites participated in the reaction and reaches the peak after 2 hours of the reaction. The electrocatalytic stability of the cobalt aluminum LDH nanoring was characterized to study the working stability of the nanoring, and we can see the result. Here, the result before and after the ADT, which is the accelerated durability test, shows that the nanoring has insignificant activity decay. And also, if we see the morphology, there is no obvious morphological or structural damage could be observed, indicating the stability of the nanoring. Finally, to conclude, we have seen how this simple but powerful cobalt aluminum LDH nanoring synthesis allows increased catalytically active sites for electrochemical ORR, and the gradient composition in the hollow LDH having aluminum content metal hydroxide will find various applications starting from energy transfer or storage to drug delivery. These are the references. And lastly, we are thankful to our professors for this opportunity to present and their patience. Thank you all for your attention.
Somadip.
Thank you, Amitabh. So it's an important. You have collected different cases, but it's important to note. I think previously we made it clear to the other candidate. You know, it's a 7 minutes presentation, and you have chosen 4 papers. Okay, and that is also not simple LDH, because you are talking about synthetic LDHs. And you are talking of different aspects of LDH modification, right? And you are talking of ESCA, you are talking of nanoring formation, you are talking of template etching, and then you are talking of ORR, right? So this is just a suggestion. When you make a presentation like this, it's important to make it short and crisp, okay? And focus on one particular topic, which you may want to consider, you know, because otherwise it becomes very broad and it's of course it's a very nice presentation what you have done. I'm not questioning that, but the way it is presented, it's very rich in volume and very dense with information, with lot of open loops and open ends. So I would just, this is one comment regarding your presentation. I would just like to ask you one very simple question, that is, the ORR over potential you mentioned is around, it's not that great, it's around 720 millivolts, right? So,
Yes.
yeah. So, what do you think? What is the reason for this high ORR over?
Sorry, sir. Can you repeat the question again?
The ORR over potential, you said, I remember, is around 770 millivolts or something like that, right? Which is a rather high ORR over potential. What is the reason for that?
Yes, sir. The reason is that because of the formation of the nano ring, there is the high surface area, and one of the thing is that the high surface area has been exposed, and second thing is that the metal metal centers also has been exposed, that actually catalyzes the oxygen reduction reaction. So in case
No. So if you have high surface area, normally you will have higher reaction. The first part of the answer was partially correct, but not completely correct. Think about it. So you are saying that it's in the nanoring, you have a high overpotential, right? So what is the origin of overpotential? That means it's difficult to drive the ORR, right? Something is happening that is making it difficult to drive the ORR, right? That is the simple logic, right?
Yes, sir.
And if you have a ring, so if you have a huge cavity, what happens when you are doing ORR? What is it that you produce in ORR?
Either H2 or H2O2.
No, you produce a reduced material that is essentially H plus getting reduced to H, right? To hydrogen, right? And then you have HH coupling, and then you have H2. Okay. To test that H2, you have this H2 combining with or H minus combining with O2 to form this H2O2. That is a separate, that is completely separate. So you essentially generate basically diffuse gas bound. So if you have sites, which is a nanoring, which is a high, you tend to block the forward reaction. So your kinetic energy barrier increases very much. Okay. And that's why your ORR shoots. So it's not a good material for ORR. That is what I want to tell. Okay. With 770
This paper has
millivolts.
been published recently in 2020. Mainly the whole presentation is based upon this first paper.
Right.
And they have also mentioned that there are a lot to develop it, this work has they have done using only, because we can in the paper I have also read that in the platinum case, because that's a perfect material for ORR, that's the efficiency is much more than this cobalt LDH nanoring. But
Right.
they have just tried to point out that from the nanosheet to the nanoring, there is this increased ORR performance.
Right. And the reason now you understand, right? What is the reason?
Yes. Yes, sir.
What is the reason?
The reason is that in this ORR performance, the over potential actually blocking there is this kinetically energy barrier which is coming up,
and why is it coming up? Because of adsorption, because you have the cavity.
Because of the cavity.
Okay. Yeah. So the take-home message is try to choose a comprehensive, simple, and a crisp presentation. Okay. So that is all my comment. But it's a good word. I'm not doubting that. But you know, you need to think about it. Okay. Thank you. I have no more questions.
Thank you very much, sir. Actually, we are just learning for the first time, and reading it, I thought that I could link with the class as you took in the GIB site, and you said that
right. No, it's very nice. It's very nice. I don't want to discourage you. Don't misunderstand me. But what I'm trying to tell, I think maybe Amitavoda can explain it very nicely.
No, I think we appreciate that you are trying to build up on the topic that we have discussed in the class. We are really happy to see this one. But what Somojit was trying to tell you, when you are allocated a time of only 7 minutes, then your presentation should be much more focused. That's what he was trying to tell. Otherwise, this is absolutely good presentation. Very, 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 well covered. It clearly shows that you have understood what is LDO.
Thank you very much, sir. We
Thank you,
will
sir.
remember all this.
Yes,
Thank
sir.
you very much.
Thank you.
So, Prana, if you have no
Yeah.
question, can we sign out?
Yes, sir. Yes, they can say.
Thank you, sir.
Thank you, sir, ma'am.
So, Pratap, everything is okay?
Yes, ma'am. Condition is moderate actually.
Okay. So, you both of you can present now, and please be very careful about the time because the time is 7 minutes. Okay.
Yes,
Try
ma'am.
to try to
Jaideep will
finish.
present.
Okay, you start your presentation.
Ma'am, I am presenting.
Okay.
So, good afternoon, professors. And I hope that you and your family are staying safe and healthy. The presentation we are going to present is based on the property of thermochromism, and that is we have used the material here is chromium doped with alumina. It has got too many properties, too many advantages, because of which it is being used in thermochromic sensors. That is what we are going to study in small, like very sophisticated, very small. So, am I audible, ma'am? Can you just confirm? Hello?
Yes,
Yes,
you are
yes,
audible.
Okay, okay. Thank you. So, thermochromism is the property of substance to change color due to change in temperature, that we know. And it can be used to alert about visible damage due to overheating, or color change can indicate irregularity, and one uses about temperatures. And thermochromic sensors can be of two types. It can be of reversible or irreversible. Irreversible, it's like materials exhibits color change based on the peak temperature. The change in the color cannot be reversed on cooling, providing a permanent record. But reversible materials exhibits a reversible color change with respect to a change in the temperature. The change in the color is reversible with the heating cooling cycles. So with this property, it is used in the thermochromic sensors. So here the best example here was the chromium doped with alumina. This is because there are few advantages involved in studying this, because this chromium based chromium doped alumina, it has got high heat resistance, high melting point, high mechanical strength, high transparency, and excellent chemical stability. uh, Vanadium oxide is also good, but it has got a small this temperature, um, the transition temperature, like it's just 68 degrees centigrade, and um, it can be used only till the temperature of 200 degrees centigrade. So this was the best example till now that can be used at least till 900 degrees centigrade. So here what happens is chromium ions, they replace the aluminum ions in alumina, and that results in a compound that is known as ruby. So ruby concentration, what happens ki when the chromium concentration in this ruby is low, then the color is pink, and at high chromium concentration the color goes to green. So on heating, the color of the ruby again changes from pink at low temperature to green at high temperature. And this can be widely used in the range of 200 to 900 degrees centigrade. So if we study this in small, like briefly about the ligand field theory, here what happens at low temperature, the chromium ions, this is a little bit, it means this is bigger than the aluminum ions. So what happens ki in the stable state of alumina, when it is in a fixed state at low temperature, then at low temperature this chromium ion is a bit bigger than alumina. So when it is doped inside, it's just suffocated inside. It feels suffocated. It is like squeezed inside the octahedral cage of oxide ions. But at high temperature, what happens? The chemical bonds of this octahedral cage of oxide ions, it expands, and the chromium ions becomes more relaxed, and due to which it gives its characteristic green color. And this is what, like, the competition between these two cations to be in a proper sized octahedral cage of oxides is thus the origin of the thermochromism. Also, the threshold of the color transition temperature can be varied depending upon the concentration. Like, if we take 5% of chromium oxide and 95% of alumina, that turns from red to green at 250 degrees centigrade approx. And if we take 10% chromium oxide and 90% alumina, then that turns red to green at a range of 400 to 450. So this is just a good example, like depending upon our concentration as well as temperature, like we can gain anything, we can whatever we want, like at any temperature we take a particular concentration, at particular concentration we can take any temperature. So
Jaideep, you seem to have a internet connectivity issue.
So maybe Pratap, you can inform him, na? Just by calling him or something.
Yes, sir.
I think he does not realize.
Yeah, I'm doing this.
I'm checking it out, just a second. Sir, am I audible?
Yes.
Yes, you are.
Yes, now, yes.
Okay, sir. So, sir, can you say where I was last, like where it was audible till last?
So at the middle, we lost you basically. So when you were talking about this, yeah, a little bit up.
Yes, sir. So synthesis now.
Synthesis, we heard it. Synthesis, I think we heard it.
Achha.
Yeah. Then
Okay,
when you
sir.
were talking about this homogenization, then I think there from there.
Homogenization, yes, sir.
Yeah.
Yes, sir. Okay, sir. So the mixture of the reactions were homogenized, and they were the powders that were collected was converted into discs like tablets. At first, what was happened that only just 10% by weight of chromium oxide was taken, just to start with the experiment. Then those were heated with the in the electric furnace at this particular temperatures, 1000, 1100, 1200 and 1600 with a heating rate of this. Then the products were allowed to cool. The fire were further means they were just mixed homogeneously again. Then the red coloration were observed, like the typical red coloration, which is the property like chromium for chromium doped Al2O3 ruby, was observed at temperature more than 1400 degrees centigrade. So this was just experimental. This was to observe when it is going to give its property color. So till here it was observed that it was just green, and it started having its pink or red color from 1400 to 1600 degrees centigrade. So above 1400 degrees centigrade. Then afterwards, with different colorization, with different compositions of chromium oxide was taken, like first 10 was taken, then now 5, 20, then 40. And the tablets were again fired from 1400, 1500, 1600, because these were of no use by now. Like this was not its property. So so this was the results when the tablets were collected. This was the result. For 10% by weight of chromium oxide, chromium doped Al2O3. This was the result where this was for as soon as it was prepared, it was for 100, for 1100, for 1200, and so on till 1600. So till here it was green, till here it was green, gray, then here it was pink. So this was the property that was which they wanted to have for the further experiments. This was its property color. And here we can see that these green colors were just because of the presence of free chromium ions till then, and here it was doped. So that is why this pink color was coming. Then afterwards, this was the uh, when for particular different concentrations for 5, 20, 30, 5, 20, 10, 40. So those were again, they were seen that as soon as the temperature were increased, they were giving more brighter colors of this particular simple like sections of colors. So this was something which was the samples were collected. uh, and nothing like this was the just the results. So I'd like to hand over to Pratap.
Okay, Jaideep, thank you so much. I would like to present right now. We will basically analyze the reason behind the colors and the spectra analysis I will do. Then we will conclude this presentation. So yes, am I audible clearly and the presentation is visible? Jaideep, could you confirm?
Yes.
Yes.
Thank you.
Go ahead.
Yes, thank you so much, sir.
Only make it full screen, no? That's it.
Okay. Yeah, so now it is full screen, right? Hello? Yes.
No, it's not, but anyway, doesn't matter. Go on, because your time
Okay.
is almost up. Okay.
So the color change of the CR doped Al2O3 can be explained based on the ligand field theory of transition metal complexes. The colors of these transition metal complexes are because of the mainly DD bands, or because the electronic transition between the d orbitals is split under the electric field of the ligands. So this splitting of the d orbital is the origin of the red color of the CR doped Al2O3. So and this is the characterization. So I will first explain the FTIR analysis. So, yeah. In general, FTIR spectra of metal oxide show the peaks below 1000 centimeter inverse because of the interatomic vibration. So as observed in the graph, this graph is for the 10% weight CR doped Al2O3 calcined at 1600 degrees Celsius for 6 hours. So the spectrum showed 4 strong peaks at 782, 641, 607 and 453 centimeter, and 3 peaks. Sorry for the interruption due to the call. Thus, the spectrum showed 4 strong peaks at 782, 641, 607 and 453 centimeter inverse, and 3 weak peaks at 553, 485 and 420 centimeter. So it was the paper we have studied to create this presentation. It was reported that the bands at 786, 641, 595 and 499 and 451 centimeter were reported due to alpha Al2O3. So the presence of alpha Al2O3 was there, and the bands at 638, 607, 547 and 488 were due to the stretching vibration of CRO bonds. So in the study, the peaks at 782, 641, 607, 453 are attributed to the ALO stretching vibrations, and the remaining peaks are attributed to the CRO stretching vibration. So these results indicate that the alpha Al2O3 structure has formed with Al oxygen stretching vibration of the octahedral structure of AlO6, and confirms that the Cr2O3 is present in the system. Also, the XRD and results are not here, but as like this is that is beyond our course which is taught to us till now. So this result is consistent with that those XRD results also. And as this is thermochromism, it mainly deals with the change in color with the temperature. So UV visible analysis is a very important analysis here. So in the same 10% weight chromium doped Al2O3 powder sample are annealed at temperature ranging from 1000 to 1600 degrees Celsius, and the UV visible spectrum was analyzed. So here we can see two broad bands in the range of 410 to 461 nanometer and 561 to 600 nanometer. Those were observed in the visible range, and the two bands are associated with the DD electronic transition. So if we go into the ligand theory, there is a central metal ion, that chromium 3 plus. So those d orbitals will be split in that A2G and T1G. So the electron transition will happen from A2G to T1G, and that will correspond to the 410 461 nanometer band. And the another band, which is 561 600 nanometer, the electron transition will happen for A2G to T2G. So according to the theory of the ligand fin theory, CR3 plus in an octahedral environment helps predict the existence of three absorption bands. So the energy of the first two electronic spins allowed the transition A2G to T1G, and the other one, which is A2G to T2G, corresponding to the visible light energies. Whereas the third spin allowed the transition from A2G to T1G, correspond to the ultraviolet light that does not affect the color. So depending on the ligand field created by oxide ion, the position of these bands can be modified, which results in the synthesis of the different color sample. So that's like very short info about the UV. So UV spectral analysis, and the pink shade which we see at the absorption bands at 410 and 561 nanometer explain the existence of this coloration. And in contrast, if the chromium concentration increase, the two bands of the measured sample shifted to higher wavelengths, which we can see in the later one. Yes, so after this FTIR and UV spectral analysis, we need to prove the property of the reversible. So we on a particular concentration, we keep increasing the temperature in a particular slots. So we keep going, and we see that the compound. Yeah.
Finish quickly.
Yes, ma'am. The last slide. So. So we started from 25 degrees Celsius, and we keep heating for 5 minutes, 10 minutes, 30 minutes. So this compound retains their color in 200 degrees Celsius. Then we do the same thing for 400 for different concentration for 600. Then we cool this compound, and we see that the previous color, which was at 25 degrees Celsius, come again. So that explains the reversible thing of this heating cooling cycle of this compound. So that is a very, very important, and this has a lot of advantage in the application. So here we conclude that we have done the successfully chromium doped of Al2O3 and analyze its UV spectra and FTIR spectra, and we were able to prove the reversible property of this compound also. Yes, thank you, ma'am. Yeah.
Somojit.
Yeah, so I think they have overshoot the time quite a bit.
Yeah,
right?
they have grossly overshoot the time.
Yeah, yes. So should I still ask or leave it?
I ask one question.
Just one question. Yeah.
I have a very simple question. Why is chromium called chromium?
I think, sir, when you were teaching this topic, thermochromism, you told us that thermo means the temperature and chroma means color. So,
Okay.
yeah.
Okay, and what is the reason for these different colors? What are the normal colors of chromium that you see?
Sir, I guess normal is the green, if I'm right.
What are the other colors?
Other colors in this experiment after dropping or doping or generally?
And you can attribute them to the different redox states normally. What are the
Yeah.
color for what are the redox states? So
I
green is for
remember.
chromium,
Okay.
which
For chromium oxide, I guess, sir.
Yeah.
Green is for
No.
chromium oxide.
which redox state? Which redox state of chromium?
So maybe for like +3, I guess, because it is.
And
Yes,
blue?
sir.
Blue, sir, like I am not aware at present about the.
Okay, and the red or the orange? You have seen potassium dichromate?
Yes.
What is the color?
Color.
Okay, fine. Potassium dichromate is not pink, it's orange. Okay, orange. Okay, anyway, we stop. Okay, thank you. Yeah. For now, Amitavada, please. Yeah,
No, I am fine. No, we don't have time to ask them any questions.
Yes.
Yeah, okay. You please sign off.
Okay, thank you so much.
Yeah, Pratap. And Pratap, please take care.
Yes, sir. I'm doing actually oxygen levels are dropping, so it is being a little difficult.
Okay. Please take care of your parents, and you also be careful. Huh?
Yes, sir. Thank you so much.
Okay.
Hello.
I think they have joined. You please start your presentation, and please remember that allocated time is only 7 minutes, and 2 to 3 minutes for the question. So you overshoot the time, presentation time, where we will be compromised with the question time.
Okay, sir.
Okay, please go ahead.
Okay, sir. Is it visible, ma'am?
Yes.
Okay, ma'am. So
You
we
may
are
go
going
to
to.
full screen mode.
Okay, ma'am. Is it fine?
Okay, start presenting.
Okay, so we are. So I'm going to talk about our presentation topic, which states ruthenium complexes and their uses in medicinal chemistry as anti-cancer agents. This presentation is being presented by myself, Kumar Agendra, 18MS-121, and my partner Aina Ghosh, 18MS-211. So whenever we think about anti-cancer reagents, the first thing which comes to our mind are the most popular ones, such as platinum complexes, which have been used, which have been widely used as anti-cancer drugs for a long time, and the most commonly used ones are cisplatin and carboplatin, etc. So, but recently there have been a lot of limitations for those platinum-based drugs, because of the fact that they have a very high cytotoxicity. Cytotoxicity is the ability of a complex to poison the cell. So, of course, it's used. It is needed to a certain degree in order to cure cancer cells. But if it's too high, it may even affect different cells of our body. So that's why the platinum complexes had a high level of side effects of those drugs. So that's why the research was nowadays is being shifted to the ruthenium complexes. And why is it so? Why are we using ruthenium complexes? Is because of the fact that ruthenium
seems to have, first of all, it seems to have a low amount of cytotoxicity, and it seems to imitate iron. When iron, in the binding state, when iron binds to the complex serums such as albumin and all. So that's why it seems to stop DNA replication, and inhibit tumor cells growth. So this is why ruthenium is used nowadays, and a lot of studies are going on about its uses. So one of the most famous complexes of ruthenium complexes which are being used as anti-cancer medicine are these: NAMI-A, KP1019, KP1558, and NKP1339. So here are the structures of NAMI-A, KP1019, and NKP1339. So NAMI-A is actually considered to be a good compound, and since a lot of research has been going on about that compound as well, since it seems to link itself with the DNA and stop link itself with the tumor cells DNA and stop DNA replication, and henceforth inhibit the cell growth process. But it also seems to have like kind of a low cytotoxicity, a bit too low. So that's why the researches are still going on about it. So, and apart from that, KP1019 and NKP1339 are being used a lot because they seem to imitate iron, well, like in the same way in which iron links to serum transferrin, which actually transports iron into our plasma. So that's why they kind of imitate the same thing. So that's why they are actually better. So yeah. And the next thing comes up is synthesis of these complexes, which my friend Nanak will explain. So thank you, ma'am.
Good afternoon, ma'am, and thank you, Kumar Nagendra. So I want to share my screen. Is it visible?
Yes.
Okay, thank you. So as my friend was discussing, these complexes are the most widely used complexes in our recent clinical trials. So I would say NAMI-A is anti-angiogenic and anti-metastatic, shows anti-angiogenic and anti-metastatic activities in secondary tumors, and KP1019 also giving us a great hope. I would like to go for 6 half sandwich based arenes. This Raptus family mainly contains PTA, and these are the eta5 or eta6 complexes, mostly eta6 complexes, and these are also very sensitive to cancerous cell only. That's why our recent study also happening mainly on Raptus family. So I'd like to go to synthesis of this complexes is not very tough. We mainly use ruthenium chloride reagents, and we can synthesize.
Better skip the synthesis and then go to the other aspects.
Okay, ma'am. Okay, so synthesis is not very important, so I will go to main important part. So how ruthenium complexes work. So at first the ruthenium complexes are injected inside a human body intravenously. So then it comes into the main bloodstream and start transporting. And for transporting, it uses mainly this albumin and transferrin transferring proteins. It comes to and after transportation, it comes to normal tissue and cells and goes inside the cell. The ruthenium complexes mainly uses endocytosis process to go inside the cell, and there we mainly use the ruthenium complexes as ruthenium 3. These are biologically more inert inside a body, inside a human body. Then this Ru3 complexes goes to Ru2 in acidic mode, very low pH, and this very low pH is only possible in cancerous cells. This is not possible in normal cells, because in cancerous cells, for more energy and more growth and more cell division, they need energy and starts glycolysis and produces lactic acid, and this lowers the pH of a cell and then gets activated, and then Ru2 goes to nucleus, then binds to the major groups of DNA, starts binding with the main groups, and main groups mainly histone sites, and then it forms covalent and non-covalent bonds. Covalent bonds are irreversible and totally destroys the backbone of DNA, and then stopping the replication and transcription. This is the this is the process how apoptosis happens. Apoptosis happens because the main mechanism of the cell is getting killed. Now I'd say, is the DNA only active, only attacking site? No, DNA is not the only attacking site, but it is the major attacking site. So I'd like to say mitochondria, lysosome, these are also attacking sites of ruthenium, because mitochondria is the powerhouse of the cell. If ruthenium, we can destroy this mitochondria of a cancerous cell, then total cell will get destroyed. Also, we in a new research, we are trying to use some ruthenium complexes which will be active on some radiation. So we can change Ru3 to Ru2, Ru2 to Ru3 according to our will. So these are the tests which are going on in human body. So it is the photoactivation of ruthenium complexes, and modern delivery of ruthenium is a great research work. They are mainly using selenium nanoparticles, gold particles, silica composite compounds to inject inside our body ruthenium complexes. And these are the referral links I have used for making this presentation. And so thank you.
Marinak and Kumar, if you just go to your presentation, the last but one slide, just before acknowledgement, you have started discussing with a ruthenium adenine complex. Okay.
Yes, sir.
Yeah, but then suddenly in the last slide, you started, you shifted to another ruthenium complex, which is known to be generate a singlet oxygen. So looks
yes,
like,
yes,
yeah. So do you want to combine both the therapy together, or it is not clear to us, I think?
No, sir.
This works in a completely different mechanism.
Sir, this AP1019 and NAMI-A, these are this has already cleared trial 1 and trial 2.
Yeah, agreed.
But this ruthenium moiety has not been used largely. They are on the
all of you join. Why did you? cannot.
We are just trying to use it. So we don't need that pH condition. We can adjust our ruthenium 3 to for this.
No, I think my question was, why suddenly that ruthenium 3BP derivative, that sort of complex, brought into the discussion? Actually, I cannot see the structure very well.
But it looks like phenanthroline and then 2NN.
Yeah, it is a phenanthroline, then is a
and then
naphthalene.
NN bonding and this bipyridyl is.
So this is a bipyridyl
substitute.
analog basically. Okay. So
Yes,
then,
sir.
when you are showing light to this sort of 3BP complex, it is very unlikely that they undergo dissociation the way you have shown. I'm a little surprised with that. You understand what I mean? The last slide.
Yes, sir. Yes,
I
sir.
don't have any question on the other part. The other ruthenium complex, it enters that cell through the endocytosis.
Because ruthenium arene
that is fine.
and bipyridyl is completely different.
But suddenly, why you want to discuss this one? Couple your discussion with this one, and along with this, the previous slide. Photodynamic therapy, ruthenium 3BP complex, they generate. When you shine light, they produce a singlet oxygen. Okay, and that oxygen is actually cause of cytotoxicity or the tumor death of the cancer cell. Okay, but you have shown a dissociation. That is, I'm a little bit surprised. They don't fall off so easily. Ruthenium 3BP complex.
Okay, sir. I'll see these things.
So you would have done better if you had not mentioned this last slide at all. You understand? You would have shown the mechanism how it is entering that, you want this to enter into the mitochondria and destroy things. Yes, up to that point was fine. But the last slide, we failed to link it with the entire presentation. Anyway,
sir.
Shomodit and Purna?
No, I don't think.
I'm fine.
I'm fine.
Okay. Thank you.
Thank you,
Thank
sir.
you, sir. Thank you, ma'am.
Thank you, ma'am. Thank you, sir.
So Harsh, Vahid and Sonam, you can start your presentation.
So,
your
this
time
is
will be 10 minutes. 10
this
minutes.
is a 3-member team, so they have a
10 to 11 minutes, right?
Yeah, 10 minutes. Yeah.
Okay, ma'am.
Please start your presentation.
Is it visible?
It's visible, you can make it full screen. Okay.
So, hello, ma'am. Hello, sir.
Yes.
Good evening, all of you. This is Rohit, and I have other two members, Sonam and Hers, and our topic is thermochromism in the ionic conductor, copper tetrahydromercury. So, what is the purpose of this project? Why do we choose this? So, we choose because we to understand the thermochromism and how to synthesize copper tetrahydromercury and study its changes in color and conductivity as the compound undergoes a phase transition upon heating. So, in this presentation, we are going to address two questions, basically. At low temperature, this compound is bright red, and at high temperature, it is dark brown. Why? And the second question is increase in conductivity as the temperature increases. So first of all, what is thermochromism? Thermochromism refers basically is a reversible color change occurs only when it's melted or dissolved in a solvent. Although this is a phase change, rather than temperature effect. So thermochromic materials, here is thermochromatic materials. Thermochromatic materials basically exhibit thermochromism, and there are two type of thermochromic materials. One is liquid crystals, and the other is organic carbon-based dyes, which are also known as leucodides. So what are liquid crystals? So basically speaking, when liquid crystals are so liquid crystals took a different color depending on what temperature they are, because they change in temperature make them move closer or further apart. Simply speaking, when incoming light waves reflect off nearby crystals and add together by a process called interference, which produces the reflection. The color of the reflected light basically depend on how close the crystals are together. Heat up or cool down your liquid crystal and you will change the spacing between them, or push them into a different phase by altering the amount of interference and changing the color of reflected light uh, through from black to red and through all the colors of spectrum. Now coming to leucodides. So leucodides leucodides are much cruder indicators of temperature than thermochromic liquid crystals. Basically, their molecules shift back and forth between two subtly different structures, known as leuco, which is colorless, and non-leuco, which is colored forms. So TL's thermochromic liquid crystals generally indicate cooled versus hot with one simple color change. So now coming to the arrangement of lattice in zinc sulfide and copper tetrahydromercurate in solid state. So the overall unit cell of copper tetrahydromercurate is tetragonal. Basically, we can see here it's tetragonal. So it's similar to zinc sulfide, where we can see this as two FCCs of iodo ions with one cube at the top of other. The iodide ions in the FCC is same as the sulfur positions in zinc sulfide here.
So any one of you can continue. Let him join.
Good afternoon, ma'am and sir. I think Rohit has lost his network, ma'am.
Fine, but I can understand. But do you have your presentation? Then you can continue.
Okay, ma'am. Okay, ma'am.
Let him join. You start your presentation and he can join.
Hello, ma'am. The thing is that we divided the presentation into three parts. He was going to explain the first part.
Okay, fine. But as he has lost his connection, can you continue?
Ma'am, I will text him or call him. Then I'll let you know. Hello. Good evening, ma'am. He's not picking up the phone. Oh, he joined.
Okay, here's
Hello. Sorry, ma'am. This got disconnected.
it's okay.
Uh, I need to present it from the beginning. I was
No, you don't need to present it from beginning. You start from where you have finished, and please be quick because your time is 10 minutes, right? For all three of you. A total of 10 minutes.
okay, ma'am. So I start from the beginning. So
Do not start from beginning. You just present your slides and start from where you have ended.
I don't know where I got disconnected. Sonam, where
Oh,
did
you
you?
got disconnected in that ionic part, the structure lattice part.
Here. In this slide.
You have to show your slides. Your slides are not visible.
You are not presenting.
Now
Okay,
is it?
skip this.
So I will explain this arrangement of lattice and zinc sulfide and copper
Please be
tetrahydromercury.
quick. Please be quick.
Okay. So basically, we have seen in low temperature copper tetrahydromercury is tetragonal cell, a tetragonal lattice. So the iodide ions basically forms the FCC, and the copper and mercury cations are in the tetrahedral poles of the structure formed by the iodide ions. At this low temperature, at this low temperature phase, the solid is brick red. But as the temperature increases, disorder happens, and this tetragonal unit cell breaks into start to deform and form a disordered cubic structure of one half of the volume of the tetragonal phase. So here we can see that the all four tetragonal sites are not occupied. Basically, it's same as the zinc sulfide, but in zinc sulfides, zinc is occupied by four tetrahedral voids. But in this case, uh, all alternate tetrahedral voids are not occupied. Only two copper and one mercury occupied tetrahedral voids. So this is this color change is the phase is this phase transition is accompanied by a color change to red brown, from brick red to red brown, and a marked increase in electrical conductivity is seen, and the band gap of this decreases from 2.1 to 1.9 with the change in structure. In this high temperature phase, the unit cell is cubic. We can see here. Okay. So now Sonam will address the other slide. Sonam? Hello? Hello?
Yes. You stop presenting now. Then I'll start.
Okay.
Good evening to one and all present here. I am Sonam Pinsobhutia, and I am going to explain the other half of the presentation. Now, firstly, I'm going to explain the ionic conductance of CO2 HgI4. The ionic conductivity which is denoted by lambda. It is the tendency of an ion to move from one side to another through interstitial spaces or defects in the crystal lattice. Ionic conductors such as the Cu2Hg(I4), it can transport a current due to its ability of the constituent ions to move in response to an applied voltage. The ionic conductor Cu2Hg(I4), it is a solid analogous of the electrolyte solutions. However, through measurement of the conductivity, we found out that the conductivity of the compound increases as we increase the temperature. The main reason we found out was that when we heat the compound, the lattice of the compound changes from a tetragonal to a cubic lattice. It was found out through X-ray crystallography that 5/8 of all the tetrahedral holes and all of the octahedral holes, which was previously filled by copper plus and Hg2 plus ions in the tetragonal, are now vacant in the cubic, which leads to the free movement of the Cu plus cations, hence increasing the charge of the overall compound when it is heated. So we'll now move on to the next part, which is the chemical synthesis of the compound. Cu2Hg(I4), it is prepared by mixing copper iodide with mercuric iodide. The synthesis is divided into three parts. We first prepare copper iodide, then mercuric iodide, then we finally mix them together to form the copper tetraidomercurate or Cu2Hg(I4). The reagents which we require is copper sulfate, potassium iodide, acetic acid, and a sodium sulfate, and mercury nitride. Firstly, we prepare the copper iodide. To prepare copper iodide, we mix the copper sulfate and the potassium sulfate in a beaker, then add few drops of the acetic acid. The acetic acid reduces the CuSO4 and potassium iodide to its constituent ions Cu plus 2, SO4, K plus, and I minus, which further reacts to form the copper iodide in the solution. In the solution, there is an excess of iodide ions. So the iodide ions can further react with this formed iodine to give a triiodide ions. This triiodide ions, which is formed in this reaction, it can act as an oxidizing agent, which can oxidize the formed product, So we add sodium sulfide to reduce the triiodide back to the iodide form. Now we cool the reaction mixture and now separate the copper iodide by simply pouring out the excess solution of the supernatant liquid. The next part, we prepare the mercury iodide. It is simply synthesized by an anion metathesis reaction in which the mercuric nitride is combined with a potassium iodide, which simply forms the Hgi2. Since this Hgi2 is insoluble, so this helps the reaction to proceed forward. Now, at the last part, we simply mix the formed mercuric iodide and the copper iodide together and heat it for a couple of minutes to give us the final product Cu2Hg(I4). So thank you. Next part, Harsh-Raj is going to explain.
Good afternoon, everybody. Pintu sir, don't discontinue. I have something problem. So please share slide number 8 and 9.
Considering the interruption, please go ahead.
Hello, Rohit.
Okay, I'm presenting.
Okay. Slide number 9 and 10.
Okay. Nine and 10.
Yes.
Oh yeah. Okay.
So there is an interesting chemistry behind the synthesis of Cu2HgL4. So when copper 2 sulfate solution that is treated with potassium iodide, a precipitate is formed. Rather than copper 2 iodide, CuI2, precipitate analyzes as copper first iodide. You can see in this reaction Cu2 plus aqueous, where electron is releasing and formed Cu plus aqueous. So by applying Nernst equation, we can E is equal to E naught minus RT by NF ln Cu plus concentration of Cu plus divided by concentration of Cu2 plus. So here N is the number of electrons and F is Faraday constant, T and R are gas constant, and T is absolute temperature, and E is a standard potential, which is the difference between the cathode and anode. So any species added to the solution that decreases the concentration of Cu plus or Cu2 plus and alters the ratio Cu plus concentration divided by Cu2 plus concentration will cause an observable change in the potential and in relative stability of Cu plus and Cu2 plus. So Pentusa, can you present slide number 10? So when Cu2 plus decreased, the observable potential become less positive. So when Cu2 plus is observed in Cu plus, there is decreased in observable potential will become less positive, that is higher oxidation state, which actually means more stable, will become more stable. And if Cu plus is decreased, observable potential will become more positive and the lower oxidation state will become more stable. So that's it from my side.
Somojit.
So that's it from all of you.
Yes, sir.
Yeah, that was it.
Yes,
Yeah, Somojit, they have done.
So you see that from the nature of my question, it's obvious I did not understand what you wanted to speak. Right? So can one of you summarize in one sentence what is it that you wanted to show?
Basically, like we wanted to see the thermochromism in Cu2 Hgi4. We explain its ionic conductance, see its structure, and explain why the copper plus is stable. Yeah, that's it.
Where copper plus is stable? In which structure?
In the
So I tell you what I understood from your presentation or what you wanted to show. You wanted to show thermochromic lyotropic liquid crystals comprising of this copper sulfide and copper iodide and mercury iodide, this type of components, right?
Yes, sir.
And then because it's a too complex topic, so it was not clear at all. That's why I asked this very naive question. Okay, because when you are talking of these liquid crystalline phases, the change of liquid crystal color is essentially what you are presenting is a thermochromism in lyotropic liquid crystals. So their word lyotropy has a special meaning, which was totally excluded from the presentation. Okay, so that means these are dispersions. And then the color will emerge because of the spacing of the mesogens. So mesogens are the ones that give rise to the liquid crystallinity. You have discussed extensively the crystal structure of the mesogen forming precursors. Okay. And then from there on, you have applied also so basically you have applied field, I think, electrical field. And then with the application of the electrical field, you have changed the population density of the counter ions or the ions in the lattices, the local lattices of the mesogens, and thereby influencing the distances between the mesogens of the lyotropic liquid crystal, thereby leading to the changes. So it's a very, very complex topic, okay? And it's too much for a 7 minutes presentation, okay? But the stitching was not proper, in my opinion. You should have given a master slide. Now, what I would like to ask you is that what is it you think, for example, can you simply understand what are the, or identify what are the key factors in this type of thermochromism and electrochromism? Because of course it has electrochromism, because when you are passing current, you don't mention it, but these are thermoelectrochromic lyotropic liquid crystals. So what are the key factors that induces this chromism in these type of liquid crystals? This is only one question, and you can answer it identifying there are 3 factors and just explaining it. That's it.
So, sir, there is one factor which is oxidation state. When an element can exist in more than one oxidation state in aqueous solution, each oxidation state will have a different thermodynamic stability.
How does this oxidation state come into picture of electrochromism or thermochromism in the lyotropic liquid crystals that you are mentioning?
So basically here, sir, Cu2 plus aqueous is releasing his first electron and it changes to Cu plus.
How does it matter? Because how are you coming to that? That is an internal structure change in your mesogen that comes much, much later. Okay. So if you are talking of thermoelectrochromic liquid crystals, can you connect how this external perturbation of the electric field influences the population density of the copper 1 and copper 2? Then you should correlate with the Nernst equation. I just want to see how much you have, you have understood. I'm just trying to see that, okay? Because it's a far too complex topic. And I think it's not really related to what we have taught. That's my opinion. So, but anyway, you please, it's a very complex topic. Anyway, please.
So when we applied electric field, that iodide ions get copper and mercury, they both.
Anyway, I just explain you very simply, okay? So when you apply, for example, a field, okay? Now, when you apply an electric field, what you are essentially doing, you are essentially changing, number one, the flux of the ions through your lyotropic arrangement of the liquid crystals. That means the counter ions will be flushed, first of all, okay? That will change in the arrangement and the relative distances between the mesogens, okay? That will induce a change in color. This is number one. First reason for change of color, because the Bragg distances are changing, okay? Number two, when you do that, you also tend to induce redox reactions. And when you are inducing redox reactions, then you are having this copper 1, copper 2 relative population density changes. That would lead to another change in the color. Okay, so these are the 2 prime reasons for the electrochromism in your lyotropic systems. So one is because of the rearrangement of the Bragg lattices, so that is mesoscopic, and one is the molecular, that is basically in the units, in the mesogen themselves. Okay, now number 3 is the thermo. Now the thermochromism aspect arises because when you are changing the temperature, you have essentially perturbed the spacing of the mesogens because of the Brownian redistribution of the solvents within. And that's how you are changing the lattice arrangement of these liquid crystals. That would change one color. Okay, so that is one reason for the color change. And the second reason for the color change is because of the electronic change in the state. You are changing the thermal profile and thereby the interlayer distances between the liquid crystalline phases. That would lead to the second change. So that's how it is called thermo and electro and then chromism. Okay, so this is one model system of thermoelectrochromic lyotropic liquid crystals. And why lyotropic? Because lyo means essentially the solvent. Essentially, it is essentially coming from the solvent. So you are perturbing the solvent dipoles and the solvent dielectrics, and thereby rearranging the distribution of your mesogens in the system. Okay, very simply speaking, that is what you have presented. But this is far, far, far too complicated and not very clear, in my opinion. But anyway, it's a tough attempt. It's good that you attempted, but it's too difficult. Okay, thank you.
Yeah, I also agree with Somojit. This is a very difficult, very interesting, very challenging, as a very difficult topic. So, and not easy to squeeze it within a short presentation. But anyway, thanks to you three for taking up this challenge. Anyway, so I think for now we are done.
Yes.
They can sign off now. Do you
Yes,
have any
yes.
question?
No, it's fine.
No.
Somojit extensively discussed.
Yeah, yeah. So please sign off, Rohit, Harsh, and Sona.
Okay, sir.
Okay.
Thank you.
Thank you. Thank you, sir. Thank you, ma'am.
Somojit.
হ্যাঁ, এদেরকে বলে কোনো লাভ নেই, আমি শুধু শুনছিলাম, কারণ এরা তিনজনেই
বলেছে, ভালো করেছে।
হ্যাঁ, বলেছে ভালো করেছে নিশ্চয়ই।
ডিফিকাল্ট টপিক বা ইন্টারেস্টিং, আর না বললে না ওরা শিখবে কি করে সেটা।
না না, সেটা না, আমি বলছি যে ওরা আসলে এমন একটু তো তিনজনই একটু সেই জন্য ওরা ঠিক বুঝতেও পারেনি টপিকটা কি নেবে, সেই জন্য বেশি কঠিন টপিক নেবে। স্মার্টলি টপিক ভালো হয়েছে, অনেক সব বেশ ভালো হয়েছে, কিন্তু সবকটা
খারাপ বলেনি কেউ। তা পড়া তুমি একটা, তোমার কি এটা এক্সেল শিটে আছে এই যে টিমগুলোর সাথে?
এই মুহূর্তে নেই, আমি ওটা একটা কাগজে লিখেছি।
তোমাকে খালি একটা জিনিস ইনকর্পোরেট করতে হবে, সেটা হচ্ছে টিমে প্রত্যেকের নাম, মানে যখন টিম থাকবে যাতে প্রত্যেকের নামের এগেইনস্টে আমরা নাম্বার দিতে পারি, তা তোমার কাজটা অনেক ইজি হয়ে যাবে।
হ্যাঁ, আমি তো ওরকমই আছে তো, যেটা ওদেরকে পাঠিয়েছিলাম না।
আচ্ছা,
ওরা পাঠিয়েছে একটা, যেটা গ্রুপ করে সেইটাতেই করে দেবো।
ঠিক আছে।
ওই এক্সেল শীটটা পড়া একটু শেয়ার করো। হ্যাঁ, তাহলে
কালকে করে দেবো।
করলে আমরা তিনজনের মতো নাম্বার দিয়ে আমরা
আরেকটা হচ্ছে যে
একটুখানি কোঅর্ডিনেট করে দিও।
হ্যাঁ, আর যদি কোনো কনফিউশন হয় তাহলে আমি সকালবেলার ইউটিউব লিংকটা, এখনকার ইউটিউব লিংকটা মিটিং এ, আর হচ্ছে যে আজকে একটু লেট হয়েছে সেকেন্ড হাফটা, ওটা হচ্ছে ওদের ইউটিউবটা আছে, যেটা ওরা ইউটিউবটা শেয়ার করেছিল না, সেই ইউটিউবটা আছে। এই তিনটে করে দেবো, তাহলে আপনাদের কোনো কাউকে নম্বর দেওয়ার সময় কোনো কনফিউশন হলে ওটা খুলে একবার দেখে নেওয়া যাবে।
আচ্ছা, ঠিক আছে, ঠিক আছে, ঠিক আছে। হ্যাঁ, থ্যাংক ইউ। ঠিক আছে, তাহলে সাইন আপ করি।
হ্যাঁ, কালকের মধ্যে বা পরশু সকালের মধ্যে পাঠিয়ে দেবো।
ঠিক আছে। সমুদ্রের চা খাও এখন? চা না কফি কি খাবে?
আমি অলরেডি চা খেয়ে ফেলেছি।
আমি একটু কফি আর কেক খাবো।
কফি আর কেক খাবে? হ্যাঁ, আরে এই অমিতাভ দা এখন অফিসে বসে আছে, ইয়ার কি হচ্ছে?
কেক জন্মদিন নাকি কেক খাবে?
না, বিকেল বেলা সাহেবি অভ্যেস তুলেছি।
সাহেবি অভ্যেস, কেক ছাড়া
আমি ইয়ার কি পাচ্ছি, তোমাদেরকে খাপাচ্ছি, কিচ্ছু করবো না এখন। কফি খেয়ে ওষুধ আনতে যাবো।
সময় মা কেমন আছেন তোমার?
ভালো না, খুব একটা
ভালো না।
না, খুব একটা
আচ্ছা,
করতে যেরকম হয়।
আচ্ছা,
না মানে কি প্রবলেমটা কি?
ওই প্যানক্রিয়াসের প্রবলেম।
আচ্ছা আচ্ছা।
আবার পরশু ডাক্তার দেখাতে নিয়ে যাবো। এই হচ্ছে, আর এই কোভিড এর বাজারে এমন অত্যন্ত ঝামেলা, ডাক্তাররাও মানে আনতে বারণ করতে হচ্ছে, না নিয়ে গেলে হচ্ছে না, তো সব হয় না হিসেব প্রসিডিওর।
তারপরে কলকাতার ভোট সব মিলিয়ে একেবারে।
আর এই কোভিড এর জন্য না রেগুলার ট্রিটমেন্ট গুলো তো 12টা বেজে যায়।
100 বার। আরে অর্ধেক ডাক্তার ভয় পাচ্ছে, অর্ধেক ডাক্তার ইনফেক্টেড, মানে ইসে ডিজাস্টার,
টোটাল ডিজাস্টার, টোটাল।
এনিওয়ে ঠিক আছে, সাবধানে থেকো।
হ্যাঁ হ্যাঁ
ঠিক আছে,
ওকে পড়া, বাই
বাই বাই।